more, huh? Getting about halfway through week number 2 here, and we're making our way through chapter number 2, which is fairly dense, with a, let's say, what's a word that's not going to scare you guys too much? Challenging ideas, maybe, right? If I say difficult or hard or, impossible, then you guys might get intimidated by it. But we're going to be talking about one of the first, let's say, little stumbling blocks here and there in Gen Chem 1, at least, coming up very soon here with naming and these kind of things. So really starting to get into the meat of things is what I'm saying, right? So chapter 1, lots of definitions. Chapter 2 so far has been kind of, what is an atom and these kind of ideas, looking at the periodic table. And we're going to start to put some applications here from the periodic table and run some calculations with that today, looking at isotopic abundance and things like that, okay? So we're quickly getting into it. I told you guys would have a quiz on Friday. I'm probably going to put that online because we're having students who are in and out and here and there and all that kind of stuff. Remember, the quizzes are not there to kind of, get you. Right? I need to take points away from you guys. That's what the exams are for, okay? Right? No, I'm just kidding. I'm joking, okay? But remember, the quizzes are there for hey, look, am I doing enough studying as it is right now? That's what the quizzes are there for, okay? I don't care. You can use your book, you can use online resource, whatever you need to, okay? Look, I'm trying to set you guys up for success, okay? But if it were me taking the quiz, what I'd say is I'm going to try and do this without any help, right? And see how I do on question number 1. If I get it fine and right and feel comfortable, what does that mean about that topic? I think you haven't mastered, right? We probably don't need to spend too much more time on it, right? We just need to kind of keep up with it, right? A little bit of maintenance. If you get to question 2 and you have no idea where to even start, I say, okay, I need to make a note of this and go back and look at metric conversions or whatever question number 2 is. You guys with me on this? Right? You guys following along about why I'm doing this? I know you guys have been students for a long time, right? And as soon as I say quiz or exam, you guys get kind of anxious and nervous and things, right? But my view is not to take points away from people. It's to solve problems before we get to the exam, right? Because when's the only time I can't help you? The day after the exam, right? Because it's done. What else can I do at that point? Make sense? Fair enough? So we'll do a couple of things on chapter 1 and maybe a bit on chapter 2 on the quiz there, and it'll be online through Canvas, so just keep an eye out for that. Sound good? Good? Okay, cool. So we're going to carry on looking at the periodic table, talk about isotopes and maybe some naming, just kind of depending on how far we get. All right? You guys have lab probably this week, right? Some of you guys have already had lab, I think. Right? I just found out, I think you guys are using this top hat thing now, right? Is that what it is? Okay, so that's something new this semester. So just as a heads up, if you ask me hey, Dr. H, I have a problem with top hat, my answer might be, I'll have to figure it out too. So just bear with us while we kind of get that squared away. We're trying to make things a little bit more streamlined for everyone who's running through the labs, right? Especially as our student population kind of picks up in terms of numbers there too, okay? So, but with that said, the reason why I mentioned it is if you guys are running into a problem, just drop an email to your lab professor and just let them know, hey, I think this is a mistake or something like that, and we can kind of work through that with you guys too. Sound fair? Let us know, and we can help you out. That's all I'm saying with all of this speech. Okay? Cool. All right. Let's get started with prayer then, and then we'll work our way back into the lecture here. But Lord, we thank you for blessings, from the great to the small, Lord, just from another day, just to be able to get up, to wake up, to see the world around us, to interact with our friends, to have a good meal, to learn something new, Lord, from all these things that I start to take for granted. Lord, we just pray that you open our eyes to those things again, and just help us to see you in all of these things, Lord. We know that you're present, we know that you're here, we know that you're with us. Lord, just help us to be active in looking for you, Lord, so that we can seek after you. Lord, we pray that you just give us the strength to follow you. We pray that you just give us the wisdom to understand how you're speaking to us today, Lord. And we just ask all this in your name. Amen. All right. So, man, it was really hot in this room. Anyway, so we were talking about the periodic table, and we were discussing about how it's kind of laid out. And this is going to be one of these key things. Remember, I said that chemistry has a language unto itself. And part of the challenge, right? Part of the challenge is that I have to explain that language And we're going to have to use that language to describe some of the math that we have to do, right? And that's where the challenges come in with general chemistry, okay? One important thing, extremely important thing, is just the broad layout of the periodic table itself. There are three broad classifications for the elements. There are metals, nonmetals, and metalloids, okay? For the most part, okay, we're going to spend a lot of time dealing with the metals and the nonmetals. In a little bit, we're going to learn about how to name things. And one of the first things we need to be able to classify when we name things is it a metal or is it a nonmetal? How are you guys going to figure that out? Look at the periodic table. Got it? The nonmetals are on the right-hand side. The metals are usually everything else. Okay? So kind of this stair step here, starting from carbon all the way down to radon. That's kind of the limit there of our nonmetals. Good? We're going to talk about in just a second let's say some of the properties of metals and nonmetals. Okay? But there it is. Metalloids kind of live in between there. We'll mention it briefly here and there, and just kind of how we deal with those. But like I said, step number one, metals versus nonmetals. Okay? Cool. In fact, I think most periodic tables kind of have that delineation there as it is. So. All right, so this is an extremely important slide, although it's not maybe immediately evident why. The reason why is because that periodic table up there is going to give us a lot of information. It's not like a periodic table of different Skittles. There's actually a reason for what that is, okay? And it's a periodic table based off of atomic radius. And that's going to be one of these key factors that I'm going to emphasize over and over and over again, okay? And what I mean with that is not just for this class, but as you guys, or as I've shared with you all at this point, I'm also teaching the organic chemistry class. It's one of these key factors in there. When you guys get to biochem, guess what's going to be important? Atomic radius also, okay? So we're going to spend a lot of time talking about radius and what importance does it have in terms of reactivity and properties of the individual atoms themselves, okay? So I just kind of put it in there because it's also colorful, and I like colors, don't you? Okay? So metals tend to be solids, all right? There's one exception for this, a pretty popular one, which I'm sure you guys can fill in the blank there. What's our only liquid metal? Mercury, right? So it used to be in thermometers and these kind of things. You guys ever played with liquid mercury? Right? I have. Might explain some of my quirks, but you know, that's okay too. It's actually a super fun liquid, right? But there are problems, you know, especially biologically with inhaling mercury vapors and these kind of things, right? And fluorescent light bulbs and all these kind of things, you know, they have mercury in them, so we have to be careful that it's not released into the environment, much less do we inhale it or get it, you know, into our blood in any way, right? But that is our only liquid metal. Okay, pretty much everything else is a solid. There's one other liquid at room temperature in the periodic table, which I think we'll talk about in just a minute. Okay, but only two of the elements happen to be liquids. The others are either gases or solids. So the liquid thing is pretty rare. Although we get to something, I think it's gallium. Gallium is number 31 right here. Okay. So gallium is one of our metals, okay? And it is actually really cool. You can go onto Amazon and you can order gallium. One person's thank you, right? You know? Now, why in the world would you want to order gallium? Well, it's really cool. Have you guys ever seen like the disappearing spoon thing? No? I'm not talking about when you put it in the dishwasher and, you know, it's your roommate doesn't take it out, right? So gallium is a metal at room temperature, but you can actually melt it in the palm of your hand, right? So like your skin temperature is warm enough to actually melt gallium. It's not toxic or anything like that. So you can put it in your hand, it turns into liquid metal, and as soon as it cools back down, it'll take up the form of whatever it cools down into. So they sell gallium spoons that you can put into like a glass of warm water, and it melts the spoon as you put in there, and then there are chemists. That's our look, I can't do magic, I can only do chemistry, right? So that's the closest I get to making a spoon disappear, okay? So there's some really cool demos on YouTube and things like that with gallium, right? So close to a liquid at room temperature, but not quite, okay? Metals tend to conduct electricity and heat. I think that's probably pretty familiar with most of us, right? We know, we've seen wiring for electrical components, right? We know about copper wiring and gold and all these kind of things. We're gonna talk about how much, right? We're going to talk about how to calculate how many electrons or what voltage is being conducted in the second semester of Gen Chem. So we'll talk about electrical conductivity more then. Heat we'll talk about this semester when we get to chapter 5, I believe is what it is. The thermodynamics is what it is, okay? They have some physical properties. They're ductile, they're malleable, right? We can kind of shape them into different things, right? Aluminum foil might be a good example of that, right? You know, pretty much everything that's metallic, you know, probably even in this room here, you know, from your laptops to the stand that I use right there, right? They probably have aluminum in there in some shape or form, right? Very, very, very important metal that kind of makes modern life go. For the future, right? Not too distant future, but also kind of perpetually future for chemistry. They tend to have low electronegativities and lose electrons. We're going to talk about exactly what that means, but you're going to start to see me talk about that property over and over and over again. Why am I mentioning this to you all right now then? One of the first things that we're going to have to be able to classify is it a metal or a non-metal. And as soon as you classify something in a metal, right, we can start to think about these different properties that come with it. They tend to be solids, they have low electronegativities, yada, 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 all that kind of stuff there. Okay? Sound good? That's the language I want you guys to start to bring out when you're looking at the periodic table. Even hydrogen can be classified as a metal, although you have to get it down to 14 Kelvin. Is 14 Kelvin pretty cold? Yeah. That's only 14 degrees away from absolute zero, right? So practically speaking, we're not really going to get anything that low, right? Especially, you know, unless you have very, very, very specialized equipment, right? But even hydrogen has some metallic properties if you put in the right conditions there. Okay. Non-metals occur in all physical states, solids, liquids, and gases. Okay. Carbon is a non-metal. It is a solid, right? You guys know the different forms of carbon, right? Right? Your graphite in your pencil, even though we call it pencil lead, of course it's not actually made out of lead. That is a solid form of carbon, right? We can have different forms of carbon also, right? So we can have diamonds. Diamond is a form of carbon, and we can have carbon nanotubes and carbon nanowires and things called buckyballs and all this kind of stuff. And those are all allotropes, which I think there's a slide of later, okay? So we have solids, but even the solids can come in different forms also that have different properties. Liquid, right? So our other liquid at room temperature is a non-metal. So we know mercury is a liquid. Does anybody know what the other liquid element is? One of these fun trivia questions. Bromine, right? So bromine is in the middle of our halogens, which is going to be a very important set of elements for us. We do a lot of chemistry with our halogens. But bromine is the other liquid at room temperature. Anybody drinking a Diet Mountain Dew in here? I don't think so. Okay, so if you take a look at, why in the world would I mention that with bromine? Well, they don't have liquid bromine in there, right? But there is a reaction that you guys will learn in organic chemistry where you use liquid bromine and it makes one of the ingredients that goes into Diet Mountain Dew, right? So if you take a look on it, it says brominated vegetable oils on there. Why do they use brominated vegetable oils? I can't answer that for you. I'm just saying I've noticed that on the label itself, right? And we'll talk about how bromine works and why it's cool and why it's important as we go through, okay? But there you go, two liquids. Gases are going to be predominantly what we'll see, though, especially coming up in a slide here. I'll talk to you guys about diatomics. But we can see all different states with non-metals, right? Oh, I had the answer up there, crap. And only one person got it anyway. What's wrong with you? All right. All right, so anyway, there it is. I didn't even catch that. All right, I got to take that on my notes for next semester. All right. They tend not to conduct electricity, although that's kind of incorrect. Carbon, especially nanotubes and nanowires and these kind of things, that's actually a huge area of modern research. How we can use these non-metals to conduct electricity. Carbon's got some amazing properties, right? Although you guys might be aware of this already, we have an entire year that we tell you guys about the science of carbon. What's that one called? Organic chemistry, got it? Right, so that's why it takes a year as an undergrad, and when you guys all go to graduate school for chemistry, right? Especially if you go for organic chemistry, you guys will spend another 5 years studying it there. And then the rest of your lives just looking at carbon. Sound fun? One person again, thank you. That's okay, right? I'm happy with just one, that's all I need, so. Okay? As a quick, I'll talk to you guys later about that, otherwise I'll just ramble on, as professors kind of do, right? What do we need to know? Higher or high electronegativities tend to gain electrons, but can also share electrons. So there's going to be a couple different properties that come out of this. What you will notice if you're paying close attention is that metals and nonmetals have opposite properties to them, right? One has low electronegativity, one has high. One tends to gain electrons, one tends to lose electrons. What does chemistry? Electrons do, right? So it's kind of important to know what can gain and lose electrons because that can help us predict what reactions are going to happen, okay? But there we go, there's our nonmetals. Just real quickly, our metalloids. We can do some pretty interesting things with them, especially when we're talking about conducting electricities and semiconductors. There's some silicon right there, pretty important for the modern technological age, right? Silicon semiconductors, although more modern semiconductors are moving away from that, or at least hybrid materials. I think I shared with you I'm a crystallographer by training, and so I just love looking at crystals of things. There's our buddy stibnite. So if you take a look at the periodic table, there's kind of an oddball in terms of the naming, right? So antimony, right? Antimony here, its chemical symbol is SB, right? That's always one of those that jerk professors put on exams, right? Got them, they didn't know what that one is, right? But antimony is SB, and it comes from the naturally occurring form in nature there is what it is, right? So when they discovered antimony, I think for the first time, they got to name it, and they called it stibnite, and that's where the SB came from, right? But antimony is actually pretty important for conductive materials too, right? Non-aqueous electrolytes, which sounds kind of fancy, but it's more these more modern battery technologies where we tend to see antimony used quite a bit in modern research. Okay? They're shiny like metals, so they have some properties of metals. They conduct electricity like metals, but not as well. So that's why we call these kind of metalloids. They share properties of both ends. Some metal-like properties, some non-metal-like properties. Okay? Do I need you guys to memorize those metalloids? Not exactly, right? But might be good to know. Okay, so now we're wandering around, okay? We're wandering around campus, and we happen upon a chunk of elemental something, okay? So when I talk about the elemental form of something, we're saying, hey, right, how does this thing exist in an ideal world where it can be an isolated material? Now, I'm trying to describe this in a way to come across that not just because I say something is in its elemental form, it doesn't necessarily mean what we're going to find outside. Like if we're digging through the dirt and we find a patch of carbon, right? We're not going to necessarily find carbon as its own as a chunk out there, right? So when we're dealing with elemental forms of things, we're usually talking about, hey, in a reaction, we add this into there, okay? And so this is maybe where some of the confusion comes from. How elements exist without being combined with something else, okay? So I have an ideal world where I just have individual elements where they can't react with anything else. That's what I'm talking about here, okay? Most of these elemental forms of things are monoatomic, okay? We're going to talk about chemical formulas and how to calculate them and look at empirical formulas and things like that. Now, when I say the word monoatomic, it's self-descriptive, right? Mono, one, an atomic atom. Got it? So if I say, what's the elemental form for sodium? It's just Na. Got it? That's what I mean by this. So if I give you a question on an exam or a quiz that say, elemental sodium is added to water, and I say, write that reaction and balance it. What I'm expecting you to know is the elemental form of the elements. For most part, they're monoatomic, with the exception of 7 diatomics. You have to know those 7 diatomics. They're going to come up over and over and over and over and over again. Okay? So let's take care of those. We got hydrogen. Can't read that. There it is. We got hydrogen. Okay. We got nitrogen. We got oxygen. We got fluorine. We got chlorine. Okay. We got bromine. And we've got iodine. Okay. 7, Dr. H, I can't remember 7 things. Okay. So part of science is looking for patterns of things, right? Where are those 7 diatomics? Where are those 7 elements on the periodic table? Is that your periodic tables open in front of you? Take a peek. Where are they? Are these 7 things randomly smattered all over the place? No, they're not. So I gotta erase my notes for my organic chemistry class here. We'll get to all that same stuff there, don't worry. So let's see, where are we? We said hydrogen, that's a diatomic, right? We said nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, right? You with me? So we got the little Tetris block there on the right-hand side, okay? Those are your diatomics, and then hydrogen. So do we need to memorize all 7 of those? Well, no, but I would be necessarily familiar with where they are on the periodic table, okay? Good. So in nature, if they weren't allowed to mix with anything else, we would find these as diatomics. So going back to the example that I said there, I ask you a reaction where I add elemental oxygen to iron and balance that reaction. When I say elemental oxygen, I'm referring to O2, not just O. Is that 2 really important? Yes, it is. Okay? So we have to remember these diatomics. Sound fair? You guys with me? So they're over there on the right-hand side at the little Tetris shape there, and then we have hydrogen sitting up in the top left-hand side. Good? All right. Everybody with me about the difference between, oops, that's chapter 1. Everybody with me on the difference between monoatomic and diatomics there? Right? I always thought this was cool, right? You can actually melt sulfur and it turns red. So, unfortunately, this is one of those things about labs. There's a bunch of cool things we can do with you guys, right? Make fires and explosions and that kind of stuff. And that's what you guys want to do, right? But we also have to make sure that you guys are learning something along the way, so we can't just blow things up and say, okay, what did you learn? What's up?
So where it says sulfur there, it has the sulfur and then the little subscript.
Yep.
Does that have something to do with the elemental form of sulfur?
Yeah, so sulfur is kind of one of those weirdo things, right? Phosphorus should be on there too. So if you can't just find a chunk of sulfur that's just S by itself. It exists as S8 or S6. So it's kind of a weirdo exception to even the stuff that we have here. So it's not a monoatomic, it's not a diatomic, it has 8 of them, right? So octatomic, right? So I don't think that's actually a thing, but there it is, right? So for weird stuff like that, I would let you guys know, right? So if that's on an exam, I'm not like, was it S8 or S6, right? I tell you guys about that stuff. But if I explicitly tell you, hey, know these diatomics, then I do expect you to know that, okay? Phosphorus is another one of those things that kind of behaves in a similar way. And the P4 is kind of the elemental form, I believe, if I remember correctly. Cool. Got it. Just as a quick this and that, right? So where do we find things on Earth? Well, we find pretty much everything on Earth. There are a couple issues that we're running into, let's say modern problems that you guys need to solve, okay? There's been a recent issue of us finding helium, okay? Now, everybody in here probably has used helium at one point in their life, right? We've had a balloon or something like that. So do you think the problem comes from we're gonna run out of balloons because we run out of helium? That's not really the problem, right? Helium is extremely important, okay? Helium is one of the most inert elements that we have. And so if we really want to protect sensitive things, we need to put it under a helium atmosphere, okay? So that's one use for it. It also, we can make liquid helium. And liquid helium gets really, 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 really cold. And that's really, 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 really important. Things like MRIs, okay? They need liquid helium to work. Lots of technical and expensive equipment takes liquid helium. So you guys have probably heard, or at least have heard mentioned, that the United States has a strategic oil reserve, right? Gasoline reserves, you guys heard of this? Okay, they also have a strategic helium reserve, right? And if things get tough, things like NASA and hospitals get access to liquid helium before everybody else does. So if you guys want to make your millions, right, and change the world, just find a way to make helium, okay? In fact, that's good homework. Why don't you guys try and figure out how to make helium by matters, right? But the question is, why is that such a problem? Okay, you've got a helium balloon. You're walking outside and you let it go. Where's it going to go? Up and away. So how do we even find helium to begin with? We can't just find it like floating at, right above the grass, right? So it's going to float up. So how does any of the helium on the planet even exist here, right? So that's one of these interesting things, right? Helium on this planet comes from radioactive decay of metals, right? So when we find uranium, we tend to find helium deposits too. So we tend to find it trapped underground where we find like oil and things like that too, right? So I'm not saying this to scare you guys or any of that kind of stuff. What I'm trying to say is, I always try and share with you guys, hey, look, the stuff that you guys are learning here start to be applied to things that we're going to be, that you guys are going to be doing after you graduate, okay? Some of you guys are going to be going on to different positions. I don't know necessarily what it is, but the reason why we make you guys take general chemistry is because chemistry is kind of everywhere, right? Even if you may not want it to be there, there's always stuff going on behind the scenes. I just want to give you guys a flavor for these kind of things is what it is, okay? So liquid helium, very, very, very important. But in terms of what makes up the Earth's crust, about 90% of it comes up from 5 different elements: oxygen, silicon, right? Iron, aluminum, these kind of things, right? Aluminum and iron basically make up dirt, right? So I was working in Tennessee before I came down here, right? And there's a bunch of red clay up there, right? If any of you guys are from that area or near that area, right? That red clay is pretty pervasive, right? So that's because they have a high iron content, and it's basically rust that's in the dirt is what it is, right? And it gets everywhere, and it's a pain in the butt to dig through that kind of stuff, right? But if you go dig through the dirt out here, right, what you're going to find is nice black, right, topsoil and then a bunch of sand, right? So not so much iron in the same form in the dirt around here is what it is either, right? So we have different forms of iron, okay? About 3 elements make up 90% of the human body. Also, oxygen being a huge chunk of it, hydrogen being a huge chunk, and then carbon, right? So pretty much these right here is what makes up most of what's inside of you, right? So we probably already know the common statement of, you guys are, what, 70% water, right? So there's a lot of hydrogen and oxygen there, right? But oxygen is found in many, 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 many different places. And that's kind of what we talk about in organic chemistry and biochemistry. Where is all that oxygen? Where is all that carbon? Where are all those hydrogens? And how do they transform, and how do they change, and how can we use them in biological systems, right? So we'll talk about that quite a bit. So that's kind of what I'm talking about with that question right there, right? Does this mean oxygen as a gas is trapped in the Earth's crust? We'll talk about why that's probably not the case, right? All right, so there's our broad overview of the elements. Monoatomics, diatomics, these kind of things, okay? The next thing we can chat with is about the idea of isotopes. They're the same element, okay? What defines an element? The number of protons, got it? So, if I have carbon, it's always going to have 6 protons. If I have an isotope of carbon, it's always going to have 6 protons. It's just going to have a different number of neutrons is what it is, okay? Now remember, neutrons don't have a charge, but they do have a mass. So as I add or remove neutrons to make different isotopes, I'm changing the mass of that specific atom, okay? So what we're going into is, what are the numbers on the periodic table, and what do we use them for? So if you take a look at the periodic table at the bottom, right, you guys see a couple of numbers that have some decimal places with it. That's what we're going to start to figure out how to calculate and how to use. And we get those numbers because there are different isotopes, okay? So here are the 3 isotopes for hydrogen. Predominantly, we end up using hydrogen. That's what we drink if we have a glass of water. Although there is some deuterium, right, that kind of exists naturally too. Okay, if you guys have ever heard of heavy water, has anybody ever heard that before? It's something that's used in nuclear plants, right? We also use it in the organic chemistry lab, okay? Deuterium is hydrogen with an additional neutron, right? So 1 proton, 1 neutron. Now why is deuterium so useful for us? Well, hydrogen's the smallest element we can get, right? It just has 1 proton and 1 electron. If I add another neutron to a hydrogen, I double the weight of it, right? Because I'm adding basically another neutron to it. Why is that important? Well, we can actually measure the difference of reactions, okay? We'll talk about this more later, as I keep saying, as I love to say, right? But when I teach you guys organic chemistry, or when I teach you reactions, your first question should be, Well, how the heck does this guy know that happens, right? Well, okay, maybe he read the textbook ahead of time. I did it. Okay, I'm just kidding, right? How do we know that reactions happen? We have to have a way of proving it, right? I can just tell you things happen. You guys are like, yeah, he looks trustworthy enough, right? Yeah, sure, okay? But having these kind of isotopic tricks, where does a pharmaceutical go when you ingest it, right? If you're taking something for acid reflux, where does it go in your body? Well, we can use isotopes to kind of track that stuff, okay? And so we can see if we actually can get the right medication to the right spots, right? So isotopes are going to be extremely important. And it's because, part of the reason is because we can change the mass of these isotopes too, and that's really important for deuterium, okay? Tritium, we don't talk about really too much at all, but it's extremely important for anyone going on in the medical field. So you guys will talk about it a lot there, okay? All right, so this is another one of my favorite periodic tables, right? So if you guys, I know it's kind of an eye exam for some of you there, but remember my notes are online for you guys, so you can just pull it up there. So this is a periodic table laid out by isotopic abundance, okay? So the little bars that you guys see in here, this is a relative percentage of the different isotopes that are available for the different elements on the periodic table itself, okay? So, for instance, if we go up here, I know it's going to be kind of blurry and stuff, right? So there's our buddy carbon, right? You see one big bar of carbon right there, right? That's for carbon 12. That's the most abundant isotope of carbon in nature. But you guys see that small little bar next to it? That's for carbon 13. Carbon 13 exists less than 1% of the time, but it's really, 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 really important, okay? Carbon 13 helps us figure out the structure of different molecules. We can do a technique called NMR, and we can use carbon NMR to figure out the different structure of things, okay? So what I'm saying is this. If we're in this magic world where we just have elements around, and I find a patch of carbon, and I pick up and I scoop up a handful of that carbon, 99% of what I'm holding is going to be carbon 12, and about 1% of it is carbon 13, okay? So what we need to figure out when we represent this on the periodic table is the weight, okay, of those isotopes and, right, relative to their abundance. So I need to know the percentage of that they exist and how much they weigh. You guys with me on this? And that's what we're going to be doing with the math. So I need to know the relative percentage and how much they weigh. Okay, so those are two important bits of information. Okay? And you can see things like silicon, there's 3 different isotopes there, et cetera, okay? See something like molybdenum there, right, number 42, there's a bunch of different isotopes that come out of that one, right? So that's a very, very, very important element, molybdenum too. All right. Okay, here we go. So for most elements, the percent abundance, oops, I was about to write with my eraser, that'd be fun. Percent abundance. The percent abundance of its isotopes are constant. That's what I'm talking about. You take a scoop of carbon anywhere on this planet, we're going to see 99 to 1, right? Carbon 12 to carbon 13. Okay? That statement there that's underlined is important. The periodic table lists or displays or shows, whatever you want to say there, right? The periodic table displays an average atomic weight, okay? So it's the weight of carbon 12 times its percentage, plus the weight of carbon 13 plus its percentage, okay? And that's the atomic mass, okay? So this is the equation that we're going to be working with here, right? To calculate atomic mass, I take the sum of the fractional abundance, the percentage, right, times the weight of it, right, times the mass, and I just add those up. So if I have 15 isotopes, I need to know their percent abundance and how much they weigh. I multiply the percentage times the weight, percentage times the weight, percentage times the weight, and I just add those up. That's all we have to do. Pretty easy, right? So we just have to understand percentages and we just have to understand addition. Not too bad with that. Sound good? Here's our buddy magnesium, right? Number of protons is constant, number of neutrons change, the mass changes, right? We got a question coming up on magnesium, is what it is. Everybody got what they need to from this slide here. All right. Before we get to the magnesium thing, let's do let's start with a nice, straightforward example, okay? Typical question on an exam or a quiz. Sorry. Okay. One of these typical questions, got it? Okay. Calculate the percent abundance of something. Calculate the isotopic mass of something, those kind of things. Boron occurs as a mixture of boron 10, and I give you a mass, and boron 11, and I give you a mass. Okay? Boron 10 is 19.91% abundant. Calculate the atomic weight of boron. Okay? The atomic weight or the atomic mass, either way. First things first, we need to start to break apart and gather out our information, right? So boron 10, right? For boron 10, we're given our mass, and we're also given our percent abundance. Good? So we're given mass, we're given abundance. Boron 11, we're given our mass. If you take a look back on the previous slides, let me scroll back for just a second, okay? Or we'll give you just a second to copy this down. What information do I need? I need abundance and I need mass, right? I need 2 bits of information for every isotope that I have. You guys with me on this? Do I have 2 bits of information for boron 10? Yeah, I've got the abundance and I've got the mass. I have the mass of boron 11. Do I have the abundance? Yes, I do. Do you guys see it? It's up there. Do you guys see the abundance for boron 11? What's the assumption that we're working on? And it's a very good assumption. Everything has to add up to 100%. You guys with me? I tell you there's 2 isotopes. If one of them is, 19.91, what does the other one have to be? 100 minus 19.91. You guys with me on this? So it's not explicitly stated, okay, but it's implied. So for boron 11, right, 100% minus 19.91%, that is 80.09%. Good? Now do I have abundance and mass for all the isotopes? Yes? Okay, see if you guys can get to the atomic mass then. Using the formula on the previous slide then. There's my percent abundance, and there's my mass for both of those. So see what you guys come up with. Remember, we're dealing with with percentages, right? Percentages. So it's not 80 times 11, it's 80% times 11, right? Everybody with me on that one there? Be careful. Alright, so what we're going to have to do is add up the stuff for boron 10 plus boron 11, and that's going to get us our atomic mass or our atomic weight. Right? So let's do that. Right? I'm just using that equation right there, right? The sum of. So fractional abundance times the mass. Fractional abundance, 0.1991, right? Times the mass, 10.0129, okay, plus 0.8009, right, times 11.0093 equals. Everybody with me, how I got those numbers? Do you guys see how I'm dealing with the percentages there, right? I just turn them into fractions. That's all a percentage is, right? What you guys get as an answer? 10.81. 10.81. Sounds good. Okay. Cool. Is that right? Yeah. Hmm? Units would be good, right? So 10.81 what? What are the units that we have? Are percentages a unit? No, what are the units we have? AMUs, right? That should be easy for all of you to remember, right? Ave Maria units, we got it? Okay? Just kidding, okay? Is that answer right? How do we know? Did you guys know you had the answer in front of you the whole time? Where's boron on the periodic table? What's the number at the bottom of the box with boron? What is it? That's got to be a coincidence. There's no way that could be the same thing, right? What's the number at the bottom of the box for boron? 10.81. You guys with me on this? Do you guys get to understand the point that I'm trying to make? Okay? We are calculating that number on the bottom of the box on the periodic table. That's all we're doing. What do we need to do that? The percentage and the weight. Good? So if you're on an exam, okay, and I ask you, hey, right, calculate the atomic mass of boron. You go through, you show me your work, and you can always know that you got the right answer because the answer is on the periodic table. And you will have the periodic table on the exam. Sound good? All right. Do something a little bit trickier, right? All right, see what you guys can come up with here. Maybe I'm getting hungry is what it is. You're making me nervous, don't worry about it. So, got a little bit of time to look at it here. What information are we missing? Well, we need two things, right? We need abundance and we need mass. We've got that for two of them. That's kind of laid out. But we need to figure out abundance and mass of magnesium 26. So we're missing two things for magnesium 26. Got it? Can you guys figure out the abundance? Yeah, that's not too bad, right? Everything has to add up to be equal to 100%. All right? Stop here. It is. So for magnesium 26, let's just do that in black, I guess, right? So 100%, right, is equal to the abundance of 78.70, right, minus, plus 10.13% plus X, right? You guys with me on this? So figuring out the abundance of magnesium 26, right, X is equal to 11.17%. Right, so we can fill that in right there. Good? Now we're still missing the mass. So we got black, we'll do this part in blue, right? And we'll do this one in red, okay? So how do we set this up? So percentage, 0.7870, right? Times the mass, 23.985, okay? Percentage times mass, good, plus percentage, 0.1117 times, we'll just do it as, what letter do we want to use? Q, okay? Doesn't matter, okay? We don't know what Q is. Q is this right here, our mass, right? We're trying to figure that out. You guys with me? What does all this have to be equal to? How do you know it has to be equal to 24.31? Because it's at the bottom of the box on the periodic table, right? You guys with me? Got it? Can you guys solve for Q? Okay, solve for Q. Give me an answer. What's up? What's up, man? You just watch me do it? Am I that amazing? Thank you. Looks like you guys are all getting there. A little bit off. Go back and check your math through there. That's why I strongly recommend writing this stuff down. Oh no! That looks good. How's it going over here? Just watching? Okay. Fair enough. All right. So if I did my math right, let's see, if I did my math right, just to kind of fill in some numbers, I did, let's see, this is 18, gosh, I do that every time. So this is 18, right, 0.876, in red here I got 2.53, right? And over here we just have 0.1117 Q, right? Right, if I just simplify things, right? And then if I just do a little bit more simplification, I got 2.904 equals 0.1117 Q, right? So Q is equal to 25.998 is what I got. Good? Maybe that's where you got that number from, right? Is that what it
No, I
was?
didn't finish it.
Oh, you did? Oh, okay, gotcha. Good, everybody with me on that? Do you have to do the math this way? Yeah, because of what you get the right answer, right? Do you guys know what I mean? I don't care how you do the math, I care that you show me, right? Write out the steps that you're doing, and just get to the right answer. Good? Does my answer make sense? Does my answer make logical sense given the information that we have? Okay, well, I'm given magnesium 24, 25, and 26. 24 has a mass of 23.985. 25 has 24.986. And I calculated 25.998. Does that seem logical that we're kind of stepping up each time by about 1? So do you think my answer is probably reasonable? Yeah. Good? So always go back and check your answer. I know, like, we're always so happy, especially when, you guys know when it's multiple choice and, like, you get the answer 13.1, but the answer on the exam is like 12.9. You're like, close enough with it, right? I'm just happy I got something nearby, right? Always go back and check your answer, okay? It should make logical sense. That's all I'm trying to get you to think about with this. Now, the better question would be, the better question would be, how can I get familiar with what makes a logical answer? You guys catch what I mean with this? Right? How do you get familiar with what is a logical answer for a question? Well, that is going through and doing some practice problems, okay? Getting comfortable with it, getting familiar with it. Good? All right. Tricky time. Okay? You can tell it's tricky because it's really, really small text. Just kidding, that's not how you tell. I just have to. You guys have all the tools you need to solve this. We're not going to use any different math. All we have to do is think about what information we're given and what information we're missing, and put together and write down a logical string of equations, right? Or a logical equation to solve. Okay? That's the tricky part. You've got an equation with two variables, so you have to find a way to relate those two together. Right? So how do we relate those two together?
Yeah.
things, not really related to the other percentages. They both have to be what? There you go, got it. So see if you can select one of these in terms of the other, that's what I'm trying to get you to do. Doing jumping jacks upstairs, I guess. Okay, so what information do we have, right? So we've got an equation to be calculated using two variables in the system. So probably what I need to do an equation that has two variables. What do these two represent? Oh, yeah, for related to each other. They both have to add up to 1. Right? Well, they both have to have to equal 100, so can you write an equation that relates those two together? So if you have two variables, you need two equations. That's what it is. What's the problem with this question? What information did I not give you? The percent abundances, right? You guys have the masses. You guys can look up on the periodic table what it should be equal to, right? But I didn't give you any of the percent abundances. So we'll just do blue and red, right? So there's my information for 37 and 35. Got it? So we have percent abundance of 35, we'll say X, right? Times 34.9, 9689, right? Plus Y, the percent abundance for 37 there, times 36.9659, right? And that's all equal to 35.46. You guys with me on this? Percent abundance times mass is equal to the number off the periodic table there, the atomic mass. Everybody good on this? So now we have an equation that has two variables. So if you have an equation that has two variables, I need to give you two equations to solve, right? That's the only way that math works, right? Otherwise it's a variable, and guess what the answer could be? Whatever you want, right? Which would be great. That's a great exam question. No one can get it wrong, right? But it's a bad exam question because there's no assessment that happens with it, right? There's no understanding that comes along. How are X and Y related? X and Y are percentages. With me? So how are X and Y related?
X plus Y equals 1.
X plus Y has to be equal to 1. You guys with me? What does this mean? How in the world did we get that? X plus Y is equal to, whoops, I gave away the answer there, but that's fine too. X plus Y has to be equal to 1. They're percentages. X percentage plus Y percentage has to be equal to 100%. Got it? So now we have two equations. X plus Y equals 1, and X plus yada yada yada, Y plus yada yada yada, right, is equal to 35.46. Two variables, two equations. Can you guys solve this now? Yes. What do you need to do? You need to either solve X in terms of Y or Y in terms of X. Either way is fine, as long as you guys are paying attention to what you're doing. Okay? So watch. What I mean is Y is equal to 1 minus X. Good? Does everybody see what I'm doing here? I'm taking my simpler equation and solving for the other variable. Now I can take this and put it into this equation right here. Good? Let me rewrite everything. X times 34.9689 plus 1 minus x, right, times 36.9659. Everybody see what I did here? What's the tricky part about this problem? Finding my two equations and how to relate x and y together. Remember, there are abundances, there are percentages, they have to be equal to 1, they have to be equal to 100%. Now we have an equation with one variable, so now we just need to simplify and bring everything together. And at the end of it, let's see, I got a bad glare coming here, so I'm not just kind of squinting around. So I got x is equal to 0.7541, and whoops, I did the wrong color here, so that should be blue. I'm going to confuse you guys with that. So x is equal to 0.7541, and y is equal to 0.2459. Okay? So I know we're running out of time, which is why, but here's what I want you to do. If you can't get to my answers there, come see me, right? We just have to simplify this equation, walk through it step by step. Multiply this together, multiply these together, and solve for x is what it is, okay? Tricky problem, think about it, look through it. There's a couple examples like this in the textbook, okay? So work through another one just to kind of get it stuck in the brain there. I will see you guys on Friday. See ya.